My name is Olivier Guyon. So I'm actually joining you today, which for me in Hawaii is tonight, from the control room of the Subaru telescope. So Subaru telescope is one of the largest telescopes in the world. Behind me, you can see the computer screens. The telescope is actually running because it's nighttime in Hawaii. I'm in the control room in Hilo, which is close to the coast, and higher up at more than 4,000 meter altitude, there is another control room where my colleagues are actually running the telescope tonight. And tonight, they're actually looking at exoplanets. They're looking at spectroscopy of stars to detect exoplanets. There is here a PANOPTES unit, a real PANOPTES unit, and I'll talk a little bit about that. But before I do that, let me show you a little bit what my day job is. Okay, so my day job is, my regular job is to look for exoplanets at the Subaru telescope. And you can see a picture of the Subaru telescope on the right. So it's a very large telescope, more than 8 meter diameter. And on the left, this is an image that we took of a system with 4 exoplanets. So there are actually 4 planets circled by a little circle. And the interesting thing in that image is the star is gone because we've worked really hard to build a chronograph, so the star is gone. So that's my regular job, and it's actually very difficult. You need a very large telescope to do that. So here is a picture of the Subaru telescope. In the bottom, you can see of that picture, you can see the mirror, which is more than 8 meter diameter. So you may think, oh, to look for exoplanets, you need a very large telescope, but that's not true, actually. We're going to talk about Project PANOPTES, which is using very small telescope. And so it's a citizen science project, as Preeti described. Here is a picture of one of our PANOPTES units. So you can see it's actually very small, and you can see it here behind me. So as Preeti mentioned, the most productive way to find exoplanet is the exoplanet transit technique. Essentially, you just have to wait for a planet to pass in front of a star. The star will get a little bit dimmer, and if you can stare at enough stars for enough time, you will eventually pick up those events. Exoplanet transit, it seems easy because you're just measuring the brightness of a star, which is not that difficult. But it's actually very difficult because you don't know, if you're looking for a new planet, you don't know which star to look at, and you don't know when the transit will happen. So you have to look at lots of stars for a very long time. And that's actually a very interesting project for citizen science because professional telescopes like the Subaru telescope, they're very big, but they have a very small field of view. They can only look at a very tiny patch of the sky, usually one or a few stars at a time. So what you need is quite different. You need a wide field telescope, something that can look at a large number of stars at the same time. And ideally, you need many of them all over the world so you can follow most of the sky most of the time. And this is why Project PANOPTES is such a great project for citizen science, because it actually makes a lot of sense as a very serious exoplanet survey by itself. So when we started this project, there were really 3 challenges, 3 questions that we needed to answer. Is it possible for citizen scientists to build a small robotic telescope that can scan the sky every clear night? Because we need that to follow as many stars as possible for as long as possible. Can this be done in a simple way that's affordable, that's not too expensive? Can we use regular cameras? Can we use a simple telescope design, not using a large dome around it? And finally, can these telescopes, once they're built, work together as part of a global network, sharing and combining images so that we can follow a large number of stars? So specifically, if one of the telescope looks at a field with stars, the daytime arrives in the morning, can another one somewhere else take over that same field? So those are the challenges that we have been working on for several years now. So we started with prototype designs to see if we could build something that's not very expensive and simple enough to assemble. So here are some of our early prototypes. You can see that they look different from each other because as we started, we basically made mistakes and then we optimized and improved. And this is what we settled upon. This is what a PANOPTES unit looks like. So there's one behind me, but here's a little more detail. The main thing here, the main two things you notice is that we use regular digital cameras, not expensive professional cameras, regular digital cameras. And we also have something that does not have a dome. If you look at most telescopes, you expect to see a dome. We decided to keep it simple and not to have a dome. Just basically having the cameras in a box that's weatherproof. So if it rains or if it's daytime, they're protected. They just look down. And we did a little bit of weatherproofing so that if it rains, all of the electronics is okay. So this is our first unit being installed in Mauna Loa Observatory in Hawaii. So you can see myself and two of my colleagues assembling the unit. And you can see it's two eyes here. It's also sort of two lenses with the two cameras. And the mount is a mount that will basically track the stars at night. So here's an example of an image that this takes. So it's a very nice image. We actually were fortunate. We were looking at a comet Lovejoy, and a meteorite passed in the field. But the thing that's most important when looking for planets, for exoplanets, is not so much the comet and the meteorite. It's all the stars you can see in this image. There are more than 10,000 stars in this image. So every image that the camera takes has a very large number of stars that we can follow. Here is another image. So this is a full field image. This is a constellation of Scorpius, which is very interesting because it's got lots of stars, but it also has dust and clusters. And so you can see the full image here is about 10 by 15 degrees. That's the size of a small constellation in the sky. And if we zoom in, you can see even more details, even more stars. So it seems surprising, but a regular camera can actually take these nice high quality images. And to do that, it only needs two things. One thing, we need to be able to take a long exposure. So this is an exposure which is typically we leave each exposure is a few minutes, and we need to track the sky so that those exposures are sharp. And that's what we've done here. But that's only the beginning of the story. Now, the next thing we need to do is measure the brightness of stars very accurately with these images. And so that's something we've put quite a bit of work into. I won't have time to go over the detail, but one of the challenges was that the stars are falling on pixels of different colors. The stars have their own colors. So we've actually worked for several years to figure out how to do that. And we've demonstrated now that we can do that. And probably the best example is this. So we had a group of students in California build one of the PANOPTES unit, and from the roof of their university building, they deployed it and they looked at a star which we knew had an exoplanet, and they were able to measure to detect the exoplanet. You can see the measurement of the brightness on the right. So this basically tests that everything's working and that the system, although quite simple and not very expensive, can detect exoplanets. And then after this success, that small telescope was actually installed on Mount Wilson in an observatory that's not very far from where they built it. So you can see the team installing their unit on a tall pier because they were next to buildings. So what's next? Well, now that we've actually completed the design, that we know it works, that we know it can detect exoplanets, we are turning this into a citizen science project where multiple groups, schools, citizen scientists, can build their own. And what we're doing, Preeti, myself, and the rest of the team, is we are helping various groups build this unit. So here is a map of the world with some of the units highlighted. The green ones are the ones that are running. You can see actually there is one next to India in Bhutan, which was one of our recent deployments. So what it looks like for a team is basically they start in the lab, they will assemble the unit. So you can see a unit on the left in the final stages of building, and once it's done, they test it at night, as shown on the right here. This is a unit in Arizona, in the US. And then ideally they can put it in a place where the sky is good, and it will robotically run night after night. Every time basically the sky is clear, the unit will start taking pictures. And what we're really doing is a whole process of training students who become builders, and then once students have, or citizen scientists have completed a build, they train the next generation of builders. So here are some examples of teams we've worked with. Some of the highlighted teams here in Italy, in the middle and at the top right. Two of our members, team members, training students in Bhutan in the lower right. And in the lower left, you can see one of the youngest teams, middle school, building a unit. So we are helping citizen scientists and students build units. So I'll finish by actually showing you a little demo of how the unit works. This was prepared by one of our students, so I will change my screen. So before I do that, here is one of our units. This is a demo unit, so it doesn't have all the weatherproofing, but you can see it has a mount and it has 2 cameras and it moves. So I'm moving it, I'm using the hand paddle, but the real unit, when it's deployed, there's a small computer that will basically run it, and it will do this completely automatically. So now I'm going to share another screen. So this is actually a 3D visualization that was prepared by one of our students, which shows 3D rendering of the unit. And so this is what the unit does in the daytime. It's pointing down. So the mount is actually looking down. You can see the lenses are pointing down. And this is what we need to do so that the sunlight doesn't get into the lenses. And this is also what the unit will automatically do if it's raining. Now let's actually make it look at the sky at night. So here I actually I made the sun go down. Now we have a starry sky. Some of you may actually recognize some constellations. Here is the Big Dipper behind. And what happens then at night is the unit will start observing. So the mount will rotate and the unit will track the sky. And that's how those images are taken. So here is our contact information if you want to learn more. We have a webpage, projectpanoptes.org, and if you want to learn more about the project, you can email us at info@projectpanoptes.org.